Hello, thank you for watching this webinar, and thank you to Robert Grover, founder and CEO of databot, who is here to talk with us about making data collection accessible and also tangible for your students. Thank you so much, Robert, for joining us.
Yeah, thank you. Thank you for having me, Laurel. This is really fun to be able to share. We've got some really fun activities today that you'll be able to actually do in your classroom. So the activities are done with just a simple smartphone. You can do them with an iPad, an Android tablet, any of your regular smartphones, and they're going to be using the accelerometer that's built into your phone. So the activities that we're going to go through are really fun. I recommend doing them with your kids. They're a great, they're a great wrap-up activity for the end of the year because they're very physical, and they can also be a great kickoff activity for next school year. So a little background on myself. I've been doing STEAM education since 1987. I think it dates me a little bit, but I've been involved in all kinds of things that range from developing products like robotic products, the picture you see there on the left. I've helped design STEAM labs and maker spaces, curriculum. databot is the latest project that I've gotten involved in. My wife and I co-founded this company in 2018 and designed databot based on, over 30 years of working with kids. And we'd worked with all kinds of products, things like, Lego robotics and Fisher Technic robotics and electronics and all kinds of stuff. And we came to the conclusion we wanted something that would be very small, friendly, easy to use, but would have lots of utility. Because one of the reasons being is we got tired of hauling around giant chunks of equipment. And Databot's very tiny, but you can do all kinds of things with it. So, quick look at what databot is. I call it a teeny tiny science lab because it's loaded with sensors. And you'll see the list over there on the right-hand side. And we won't go through all of them, but I basically call them like a survey of sensors. It allows you to do, literally, you can do physics and chemistry and life science and earth science. You can do environmental explorations. And then, of course, from the data science side, you can take all of the data that you're gathering from those sensors and you can do all kinds of fun applied math activities. So it's fascinating, all of the things that you literally can teach with one device. Now, one of the things that I always like to emphasize, and this has to do with the activities that we're going to do here in a few minutes, is the physical action of interacting with data is a very, very powerful experience for kids when you're working on scientific concepts. So just the act of seeing sensor data that is in real time and reinforcing, whatever the topic is that you're working on can make an enormous impression in terms of comprehension. This example that I have on the screen is the one I share all the time. And usually when I introduce people to databot, this is what I start with. The image on the right is what the smart app looks like. That's what you'll be installing on your devices here in a little while to play with. And you'll notice that there's a bunch of icons there. If you were to tap on, for example, the CO2 icon, it would open up an experiment that looks very much like the one on the left. And then you simply connect your databot, which is by Bluetooth, and then you tap the little start icon at the top, and it'll start streaming data from the carbon dioxide sensor. So it's that easy. I've actually timed it. You literally can install the app and do this activity in less than 60 seconds. So, the idea of making it very friendly and accessible for kids and teachers is very important. Anyway, to wrap that up, the immediate feedback that I'm talking about is just having a student, for example, breathe on the databot, and you'll get that immediate spike that you're looking at there on the screen. And that is something that almost to it, I don't think I've ever seen anybody not react to it. They'll just, wow, it's right there. And that's a lot different than going through a textbook and explaining that we inhale oxygen, we exhale CO2. When you actually see it, and then you can start talking about your physiology, what could we do maybe to get a bigger spike? And that's when kids start, really interacting with it. They think about, okay, maybe I could hold my breath and I'll process more oxygen. So these are the kinds of activities you're going to get to experience in a few minutes, but that's what databot's all about. It's about making data accessible and easy. Now, there's tons of sensors and equipment that's out there. So you may already have some of this in your closet. So the kinds of activities that I'm going to show you, you can take these approaches with a lot of them and actually implement them with things you may already have. This sensor ecosystem that I've put together, I've broken the ecosystem into two halves. One half is, physical computing products. That's what you see on the left. And that's for the people who are doing coding and working with sensors with things like robots or Arduino boards or maybe the microbit. On the right-hand side, you'll see the traditional science probeware, things like Vernier and Pasco, things that you'll see in a traditional science lab at the high school level, even at university levels. databot's an interesting device because it plays across that whole, sensor ecosystem. So we've got people using it for coding on the left-hand side. We've also got people using it for, traditional science experiments that you see on the right. But one of the advantages we have is, again, it gets back to this ability to physically interact because it's wireless. You can easily take this device and put it in your pocket and go do experiments with it. Whereas with a lot of these tools, you're going to have to be bringing battery packs or things like that. So, embodied cognition is a pedagogy that talks about connection between brain and the body. And a lot of these activities that we do when we develop these things like that, the experience with the carbon dioxide just a moment ago that I explained is very physical. Kids are inhaling and exhaling and making things happen. Embodied cognition is the concept that, okay, when we do these things physically, they really become much more powerful in terms of a learning experience. So the two examples I have up here on the screen, the one on the left, the Acceleration Olympics, which is actually something you're going to get to try today, is one of those where students are exploring the nature of acceleration, which how can I get the highest level of acceleration? Is it a change in the rate of speed? Is it in direction? Is it combining those? The one on the right is a student that's doing a really interesting project called Smooth Walker, where she's trying to move with zero acceleration, which is a fantastic activity, just as an exploration of the nature of acceleration. Because typically kids, when I go through and I ask them at the beginning of a session, what's acceleration? Well, it's speed. And it's really not speed. It's a change in speed or a change in direction. So when they go through these activities and they actually realize, wow, I can be moving with zero acceleration, that, it dispels some of those common misconceptions. I have a couple more examples of embodied cognition that I want to show you, and then we're going to actually try it ourselves. And these are great examples because, again, if you've got sensors in your classroom, in your closet, devices that you can actually physically interact with this invisible world of data around us, you can replicate a lot of these. Starting with the first one on the left. Okay, this girl is actually interacting with air pressure, and she's doing that by running up and down a set of stairs and watching how air pressure actually changes with elevation. So we don't really think about this invisible force of air pressure that's pressing on us and down on us from all angles, but it's there. And databot allows you to actually visualize the air pressure in, either millibars or you can actually do PSI, where you can see pounds per square inch. One of the activities we do is have kids actually calculate, okay, if I could take the column of air on my hand and measure it, how much would it weigh? It turns out to weigh hundreds of pounds. So, these kinds of physical experiences are very visceral. The connection that this girl's making also is the connection between elevation and air pressure, that we can actually use changes in air pressure to determine height. So we'll actually measure things like the staircase and see how accurate it is to measure the change in elevation based on air pressure. So again, a very physical experience, but very powerful in terms of understanding, one of these forces that's around us. Next one on the right there is a girl measuring light intensity, and she's moving the databot closer and further away from the light source and seeing how the data changes. Okay, so as you move away from the light source, obviously it gets weaker and weaker, but there are specific mathematical relationships there that you can bring into play. So like the inverse square law, because the relationship is it's very specific, and you can calculate it, and kids can see, oh wow, I could actually predict, what is the light going to be reading when I get to, a full meter versus a half meter. The next slide is launching databots. Kids love to launch stuff. So again, gathering data from something that you are launching and applying that in a math class. We had a math teacher that had kids actually build quadratic equations based on, their catapult data. Let's see, the one on the far right is a favorite. This one's called Bungee Jumping Barbies. And if you look closely at the image on that slide, you'll see Barbie has a little databot backpack attached to her. And this one, the kids are dropping Barbie using rubber bands as bungee cords and calculating, okay, how far did Barbie drop with two rubber bands? And then how far did she drop with four? How far did she drop with six? And that uses the altimeter. Okay, so the altimeter is quite accurate. Again, going back to the measurements that we were doing with air pressure. But anyway, they gather that data. Once they have a data set, they can take it into Desmos. This was another math teacher that put this together. And she showed them how to create a regression that would allow you to predict, okay, how many rubber bands do I need to give her a thrilling ride off the second floor balcony? And again, really concrete experiences that kids, get to do with data, approaching it this way. Last couple I'll show you here, matching graphs by varying sound intensity. You're going to get to actually do an activity called match the graph with acceleration here in just a second. But if you've ever played with like a sound sensor and just tried to actually consider it like an Etch-a-Sketch, you're trying to draw, for example, a round mound or maybe a square wave, simply based on changing the intensity of your voice. That is a very physical thing because you're having to change the volume, right? The amplitude of the volume that's coming out. And it really helps you to understand graphing because, phenomenon over time, you can actually see when you're changing the intensity of your voice because you're seeing it go up and down. So all these things are really, again, very physical interactions with data, and it gets back to that embodied cognition. The last one here on the right that I'll show you, Messy. This was actually a story sent to me by one of our teachers in Oregon, and he uses Messy as a specific example of acceleration, and the kids love this. And then you can actually put, databot on your chest and sprint and measure acceleration yourself. So all these things are very real world. They're very relevant to a student's experience and makes, again, those interactions with science a lot more concrete. Last one. Okay, these are fun. These are actually a couple of the activities you're going to get to do. Okay, over on the left-hand side here, you'll see a lady jumping off of a set of stairs. And this is the Acceleration Olympics, trying to come up with the highest level of acceleration. Um, the two ladies also over here were spinning one another, trying to come up with a higher level of acceleration. So there's nothing more fun than interacting with data physically, and that's one of the great things about sensors is that if they're portable like databot, you can stick them inside balloons, you can do all kinds of stuff with them to experiment with real world science. All right, it's time. So the next few slides, we're actually going to walk through doing this yourself. There are two activities that really personify embodied cognition because kids are really going to have to be moving and shaking to do these activities. The first one that we're going to look at is match the graph. And the second one is called the Acceleration Olympics, where you're attempting to get very high levels of acceleration. Now, on the left-hand side, Visi is the app that we're going to use. And again, it'll work on any smart device. You can use iOS or Android. If you've got your smartphone, it should install immediately. And pretty much all smart devices are going to have an accelerometer on board, which is why we do these acceleration activities for things that everybody can share, because you're almost certainly to have an accelerometer on board. So these these steps right here is what you have to do to get set up. So what I'd like you to do is go ahead and download from your App Store or the Play Store, Visi. Look it up and you'll find it in there. It's spelled VIZEEY. You're looking for a very colorful, inclusive rainbow. There we go. And the other thing about Visi is stands for visualize. So visualizing data is why we named it that. So I'll give you a moment to download that. And again, I have timed it. If you got a good internet connection, it's not a very big app. It'll download and install quite quickly. Once you've got it installed, on the welcome screen, you're going to find a little plus sign, and it'll be top or bottom, depending on whether you're iOS or Android. But look for the plus, tap on the plus sign, and you're going to see two options. One is for smart experiments, and the other is for QR codes. Smart experiments, I'll just tell you as an aside, allow you to create your own experiments with your smart device. So whatever sensors you have that are on board your device, you can create your own experiments and collect more data. So again, depending on whether you're an Android or iOS person, those sensors will vary. But once you start playing with Visi, even if you don't have a databot or a sensor to connect to it, you've got sensors built in that you can experiment with. So the last step, open up the little plus sign, select scan activity by QR code, and scan the QR code that you see on the screen there. And it should bring in a collection of 3 experiments called embodied cognition. And there's an option to save all at the bottom of that set. So you should be able to just save the entire collection. It'll be there. And I'm going to move on to the next screen so we can actually go through and do the activities. I think we've got about 10 minutes left, and I want to make sure everybody gets a chance to do these. Fortunately, this is being recorded, so you can review and reverse, back up, and do this over and over again, which actually is pretty much necessary when you're doing, especially this first activity called match the graph. This one takes practice, so I will warn you. Don't get frustrated. It's something that is a very natural thing to gather data, hit the trash can and delete the data, and do it over and over and over again until you do master it. And that's one of the fun things that I like about it for kids is because they're learning a lot by doing this particular activity. Now, the idea is you're going to be gathering acceleration data on 3 axes. So I'm going to hold my phone up just to give you a visual. If I hold my phone up, flat in the palm of my hand, and I move side to side, that is the x-axis, okay? So if you're running the experiment, you'll see movement on that x-axis as you shake side to side. To run the experiment, you just tap on the little start icon at the top. You should have picked match the graph. It should open up that screen and then hit the little start button. It'll start streaming. And again, side to side will be X. Forward and backward will be Y. And then if you tip your phone upright in your hand, see, I'm getting confused because I use databot half the time too. I'm sorry. So up and down is C, side to side is Y, forward and backward is X. There we go. Anyway, so when you do this, you have to practice to get, first of all, the scale to match. So if you look on the left-hand side of your graphing, you'll notice that there is a scale that ranges. The one that you're matching says -20 to +20. But if you shake really hard, for example, side to side on your x-axis, you'll see it a much higher range. It might be, -40 to +40. So that's one of the first things that's going on. You have to learn the amount of acceleration to get it to scale within -20 to +20. And of course, this is one of the reasons you're going to be stopping, deleting and trying it again. It's a body memory thing. So I've learned, okay, this much movement is acceleration between negative and +20. So that is the first thing, is to master that so that you get all 3 axes on that -20 to +20 scale. The next thing is to be dead on with the order of your X, your Y, and your Z axes, right? So you'll notice that they are spaced out. So part of this is mastering time, which students have to be patient because they learn that, okay, to get those first spikes, I'm going to have to do my X, my Y, and my Z very quickly, and then I have to wait. So as we wait, that time kind of stacks up and you end up with a space between those initial three spikes and the first spike of the X. And this is a very, again, physical interaction with data going on. You're actually learning that a graph is phenomenon over time. And to get that particular representation, I'm going to have to pause between the X, the Y, and the Z. So there's quite a bit going on there. And it's a fun activity. Once kids figure it out, they've actually mastered quite a bit. So this is a summary of the learning outcomes, which I won't go through in depth here, but we'll send this slide deck out to you afterwards. You can look at it in a little bit more depth and think about, okay, what are the kids actually learning as they do this? Because it's an incredible exploration of just 3D Cartesian coordinates, if nothing more than that. All right, so that is match the graph. The second activity, to go back out to your main menu, there's a little arrow that points to the left in the upper left-hand corner of your screen. So to exit out of your match the graph experiment, tap on the little back and you'll go back to the main menu and you're going to see the Acceleration Olympics #2. Go ahead and tap on that and it's going to open up a screen that you see here that I'm circling right now. And you'll notice that now we don't have three axes anymore. We just have one. So what it's doing is it's combining the X, the Y, and the Z all into one absolute acceleration value. And this is great because now what you're going to be able to do is hold your phone to your chest. And this is very important. You can't have the kids swinging their arm around and maxing their value out. You want them to actually hold it to their body. So it's their body that has to generate the acceleration. And at this point, this is where you have the kids think about, okay, what is acceleration actually? And as I was saying earlier, change in rate of speed, change in direction. What can you do with your body, leaping around, twisting, jumping to get the highest value? Now, if you remember those pictures that I was showing you a few slides ago, um, we had some high school kids and teachers both figure out that, hey, deceleration is a very powerful force. And they were leaping off the stairs, as you were seeing. And those actually were some of the activities that generated the highest values. But it's wonderful because it's pure science. You're experimenting with that force and you're trying to figure out, okay, how can I maximize it? Now, the last thing about this one, it's timed. So when you actually start the experiment, it's not going to run perpetually. It's going to give you a 10-second data set. It gives you a 3-second countdown. So you'll notice on the little experiment, there's a 3.0. You tap on the start, it's going to go 3, 2, 1, and then you've got a 10-second data set. So you have a total of 10 seconds to leap around, be crazy, cavort, do whatever it is you can to generate the most acceleration. At the end of that, you're going to have a data set. And again, one of the fabulous things about Visi is that it's so simple to use for exploring data and getting kids really comfortable with data. All you have to do is tap on that graph, tap in the middle of this image right here, and it'll expand into what we call zoom mode. So now you can use your finger to move back and forth through the data. You can pinch to zoom in or zoom out. And it becomes a very natural way to explore data, and kids become very familiar with graphing very quickly. When you select Pick Data, which is another option at the bottom of the screen, you'll notice the first one is Pan and Zoom, which is the default. Switch to Pick Data, and now you can tap on data points, and it'll tell you exactly, what was your meters per second squared in acceleration at that particular time. So you can figure out, okay, that was my high point. And then, of course, kids are very competitive. They're going to be trying to figure out who can get the highest value. But very simple activity, really, in sense. But there's so much going on. Again, there's a list of things that kids are learning as they do these. A great set of learning outcomes, and the study of acceleration more than anything I love because a lot of kids really understand acceleration much more thoroughly once they have done this. There's another experiment that we do that actually includes the force of gravity in the accelerometer. So you can actually visualize G, which is great for teaching kids about, the force of gravity. There are a lot of space education people that use, these kinds of activities as well, because trying to get kids to understand acceleration and gravity and those kinds of things. So anyway, that is the end of my presentation. I think we got it done in just about 30 minutes. I'm going to let Laurel take it over now and start talking about how to actually use data and analyze it.
Perfect. Thank you so much, Robert. Really fast before you head out, where can teachers find more examples of these lessons and things that you can do with your smartphone or other devices?
So our website, there's a ton of free lessons on there. Many of them, if they're acceleration related, you're going to be able to do with your phone. So you could like go through and look at our sensor starters, our labs that are using acceleration. And some of them you're going to be able to do with your phone. Not all of them because you don't necessarily want to launch your phone on a rocket, but there's a lot of good ideas in there. And I'm a big proponent of sensor science. The more you can get kids using sensors and interacting with data, the more comfortable they're going to be with it.
Definitely. I think that these are great examples of how to make data collection and just data, which can be this really kind of nebulous topic for a lot of students that can feel overwhelming. It's a way to make it really tangible and approachable. So thank you so much for sharing these examples with us.
Yeah, thank you very much for having me. It was really fun. And
Yeah,
all right, thanks.
great. Thank you,
I will
Robert.
unshare now. You bet.
Unshare. I don't know if there's a way for me to unshare for you.
Yeah, I've lost my menu here somewhere.
No worries at all. It should be at the bottom, I would think. Or you can probably exit out of your presenter mode maybe, and that might help you if that's what you're
I think,
in.
I think that is exactly what's going on here. Let
Yeah.
me get out of here. Oh, wow, that is crazy. It's not showing up at all.
Hmm. I don't know if there's maybe I can just replace current share. I'll just replace the current share,
There
and I
you
think
go.
that should be fine.
Great. Okay. Yep. I think I just figured it out. It was hiding. All
Great.
right. So I'm going to exit and leave you to the rest of it. Thank you very much for having me,
Perfect.
Laura.
Thank you so much, Robert. We really appreciate you taking the time and effort to share all of this with us.
You bet. All right. Take care. Bye.
Bye. Okay, and now is on to my portion of the webinar, which is, Robert gave us a really great examples of how to take data collection and use it as a way to make data more accessible and tangible. And now I'm going to talk with you about making data analysis accessible for you and your students. We all come to this data analysis part of research with varying levels of familiarity with what different forms of statistical analysis look like, or what the different vocabulary involved means, or even just conceptually what it's meaning to show. And so that's the goal of this particular part of the presentation. How do you approach data analysis with your students? Which, disclaimer, so I am an educator of about 10 years, and I have some experience with statistics. I took a, biostats course in college. I had to teach it as part of AP Bio. I, of course, taught it as part of my research class, and I've also tutored in AP Stats before. But I'm by no means an expert in statistics. In fact, growing up, I did not enjoy math very much, which I know is a common experience for a lot of people. And hopefully, we can help our students to see that math is something that is entirely accessible for them. But just know that there's a lot of different ways you can approach statistics. These are the ways that I've approached it for myself and for my students that has worked for me and my students. You might approach it a completely different way, and that's completely fine. If you would like to access these slides, you can go to this tinyurl.com/wire-data-analysis, and then you can also access some of the links that I'm going to be sharing, and just take a look at the PowerPoint yourself. So some goals, we're going to define data analysis, describe its purpose, define null hypothesis and p-values, two very important vocabulary words in data analysis, and describe their purposes. We're going to differentiate between continuous and categorical variables and the statistical tests used for each. And we're going to practice using Google Sheets as a tool for data analysis, which I highly recommend. You don't have to have R or some super expensive or complicated statistical analysis tool. You can absolutely use Google Sheets. You can use those more complex tools if you're familiar with them and you would like to, but it's not necessary for all projects. Google Sheets does a really great job of doing the majority of what you'll need to be doing, what your students will need to be doing. So, what is data analysis? Data analysis, put simply, is the process of organizing and interpreting information gathered through testing a hypothesis. It could look a variety of different ways depending on the data that your students are collecting. In many cases, is demonstrated in the form of various types of graphs, and that is absolutely a part of data analysis. And additionally, on top of that, we'll also talk about statistical analyses you can do to demonstrate the statistical significance that is shown in your graphs. But by and large, the purpose of data analysis is to provide the basis and evidence for your conclusions. You got to have something to base your conclusions off of, and also to back up those conclusions that folks can reference in order to demonstrate the validity of what you're concluding from your experiment. So the first thing that I love to do with students is actually an activity that was shown to me as part of a professional development I did at Rice University, what's called the Rule Finder activity. So I present the students with this pattern of numbers, and I tell them that their goal is to find out, to discover what is the rule for the pattern of numbers. And the way that they can try to figure out the rule for the pattern of numbers is I put them into groups. And as a group, they will decide on three other sets of three numbers that they're going to test. And I will tell them whether or not it follows the rule. So those are the little experiments, the little tests that they're running. And I do it where they're in smaller groups because I find that that's easier than trying to do it as a big whole group. And they're able to discuss with each other. But I don't tell the whole group every group's tests, if that makes sense. I go over, they'll raise their hand when they have another set of numbers they want to try. And I'll go over to the table and I'll kind of secretly, they'll whisper to me what they're testing and I'll tell them. Just so that the groups aren't influencing each other. It just makes it go a little more smoothly. Then, after the end of their three tests, they will draw a conclusion about what the rule is for the pattern of numbers. And most often, what will happen is students will test something like, ooh, let's try 3, 6, 12, right? Because they're thinking it's doubling each time. Okay, 3, 6, 12. And they come over to me, or I come over to them, they raise their hand, and I say, yes, it follows the pattern. Oh, okay, great, great. Well, what if though, what if we try like bigger numbers, and they'll say, well, we got to be extra certain. So then they'll try, okay, with bigger numbers, maybe 12, 24, 48. And I'll tell them, yes, that follows the rule. That follows the rule for the pattern. And they'll feel really confident and they'll be like, you know what? Yeah, well, I guess we've got one more. I mean, we're pretty sure we know the pattern, the rule, but let's just try one more. Okay, let's try like 1, 2, 4, because that, maybe that includes an odd number too. So 1, 2, 4. So then I come over, they say 1, 2, 4, and I say, yes, that follows the rule for the pattern. And they think they've got it. Okay, the rule is that you got to double the numbers each time. You're doubling the numbers. But that's not the rule. The rule is just increasing numbers. If they had tried something that wasn't doubling the numbers, let's say 1, 2, 3, they would have found that that did actually also follow the rule. And sometimes you will have students that think about that think to test things that don't follow the rule that they have in mind. But most of the time, the vast majority of the time, students are going to be testing things that they think follow the rule that they already have in mind. They see this, they think, doubling numbers. Or maybe they think, oh, even numbers. Whatever the case is, they're going to most of the time try things that fit that rule that they have preconceived. And that is the entire point, because that is a demonstration of confirmation bias. And this is why it is so important that we not only demonstrate, graphically what our data looks like, but that we also do statistical analyses in order to ensure that our conclusions are not being influenced by confirmation bias. We need to do additional statistical testing to help us with that. And has a confirmation bias, as defined by Encyclopedia Britannica, is people's tendency to process information by looking for or interpreting information that is consistent with their existing beliefs. And so this is so important to bring up to students, not just when they're at the data analysis phase, but I even bring this up to them when they're coming up with how they want to test their experiments, because it's really important that you are testing not just what you think will work, but also things that you don't think will work. And one of the ways that statistical analyses address this in science is through the concept of a null hypothesis, which is defined by National University. Null hypothesis states that there is no difference between groups or no relationship between variables. The null hypothesis is a presumption of status quo or no change, right? So I'll use the in from null to reinforce no. So null, no change, or null, no difference, right? And so in science, instead of saying we've proven a hypothesis, we say we can reject the null hypothesis, or sometimes we have to accept the null hypothesis, right? We have to be able to reject the idea that actually there was no change. So we have to reject the opposite of what we think. Because in most cases, if you're experimenting, you're anticipating some kind of difference, right? If you're doing some sort of clinical trial with a new medication, you're anticipating, you're hoping that there will be a difference, right? That there will be a difference once patients, there will be a difference in outcome once patients are provided with this medication. That is what you're expecting. That's what you're hoping. But instead of just confirming that and saying, oh, it worked, you have to be able to say that it was significantly different from some other group or from the null hypothesis saying that there's no change. And you can also bring in this concept of confirmation bias when talking about placebos or control groups as well. So it's really important. We're not proving a hypothesis. We are rejecting or sometimes have to accept a null hypothesis. So how do we know when we are able to reject a null hypothesis? Well, we have this handy dandy term, the p-value. And the p-value is the probability that the observed effect within the study would have occurred by chance if in reality there was no true effect. So essentially, the likelihood that the null hypothesis is true. So we want the p-value to be low. We want there to be a low possibility that actually there was no difference. Actually, there was no change, or any change, any difference that we see was actually just purely by chance and not because of the variables that we were testing. What is an effective, or what is the p-value that we can use to say that we have rejected the null hypothesis? That will vary from statistician to statistician and from experimenter to experimenter, experiment to experiment. By and large, when you're doing these things with your students, you can assume that a p-value of less than 0.05 or a 5% probability that the null hypothesis is true is good enough. Okay, if you have even lower than that, even better. But generally speaking, a 0.05, less than 0.05, is saying that you have at least a 95% probability that the data show a statistically significant difference. And I also want you to emphasize with your students that sometimes you don't have a statistically significant difference, and that's okay too. You've still learned something from that. The importance is that you're able to quantify your confidence, and that's what these statistical analyses do. So yeah, how do we determine the p-value? We're going to run some statistical tests. Okay, so full disclosure that this is showing how long I've been doing this, but 10 years ago, I found this graphic from practicallyscience.com. I tried to find it again. It does not seem to exist anymore. Someone else has purchased the domain, but I still think that this graphic is useful. It was useful for my students. It was useful for my classes, and I hope it will be useful for you. The examples that they're showing here are in a clinical trial kind of example, testing different medications, a new cancer drug, and its effectiveness is what they're showing. Disclaimer, your students should not be administering cancer fighting drugs to people, but this is just an example to show the difference between the types of variables you might be testing. So I use this also to teach students about the difference between categorical and continuous types of data. So categorical being exactly what it sounds like. You have categories, right? In the first example under the Fisher's exact test, their categories for the independent variable are giving the drug to the patient versus not giving the drug to the patient. And those are just two categories. Either they've been given it or they haven't, right? Maybe the haven't is a placebo group and the have is the experimental group. Okay. Those are two categories. And then with the dependent variable, maybe you're testing or you're measuring rate of survival after 5 years post treatment or from receiving the treatment, something like that. And so that once again is a category, right? And so in if you have two categories, you have an independent variable that's categories and a dependent variable that's categories, then you're going to do something like a Fisher's exact test, which you can find a lot of these tests online available for you, which is really helpful. Or if you want your students to do each of the individual calculations, you can find also online explanations for all of these things. Um, then let's go to the student's t-test example. This time, we still have our independent variable as being categories, right? Either they are not receiving the drug or they are receiving the drug. But the difference this time is that the dependent variable, what we're measuring as the effect, is instead of just rate of survival, we're looking at the actual tumor size and whether or not that has reduced or grown. And in that case, that is a continuous variable. How I describe continuous variables to students is imagine you have a number line, right? And you've got 1, 2, 3, 4, 5. If you could have something that if you could have a result that falls in between those numbers, it's most likely a continuous variable. The size of the tumor, it might be 1 centimeter, but it could also be 1.5 centimeters, right? Versus the having the drug versus not having the drug, you don't have a group that you don't have on a number line someone that's receiving that's 1.5 receiving it, right? Either you have it or you don't. Now, the way that you could make that a continuous variable is then in the regression analysis example, where you have a dose for the drug. So this time, maybe you're able to give them 1 ml, but you could also give them 1.5 mils, right? It could fall in between the numbers on the number line. And that's how I typically explain it to them, and that's worked for them. I think what works really well, though, especially, is like exactly what Robert was talking about, having them experience data collection and experience what those different types of variables can look like. So I've put for you here on this slide, I've put a worksheet that I've provided my students for choosing their statistical tests, which goes through all of this. Also, making graphs in Google Sheets with standard error bars, which is another way. So you see these bars that are on there. Those are standard error bars. And the error bars, then, if they aren't overlapping, that shows a statistically significant difference versus if they are overlapping, then it's likely not a statistically significant difference, assuming that you're using a 95% confidence interval, which that Google Sheets link will show you how to do. And then finally, the other link that I have on here is an M&M's chi-square analysis practice, which I actually did, I believe, at a one of the society's research teachers conferences when I was a teacher. And I remember being shown this, and this is so fun. And students love anything that they also get to have a snack after doing it. And so M&M's chi-square has always been a huge hit, and it makes it really tangible for them so they can understand, okay, this is an example of a chi-square test and when I would need to use a chi-square test. But what we're going to do is we're going to practice using a t-test. And this is something that I have done with my students. And so you can go to this tinyurl.com/t-test reaction, and it will bring you to a prompt to make a copy of the Google Sheet that I have made for us. And I'll just go ahead and go over there right now. So on here, which it might be hard to, let me see. There we go. It's a little better. I have for you an example of an unpaired t-test. Um, and this is the data that I actually collected with my students a while back. I had 10th graders and 11th graders in my research class, and so I had them test their reaction times and we compared them. Those are two completely different groups of students, so they are unpaired, right? And then we followed the exact things that I'm going to be showing you. The graph making is in that link that I mentioned on the slide. So if you want an explanation of how to make a graph like this, you can follow that. I've also provided an example of the paired test in case you need to look at it. But if you want to do it yourself, this is where you will go. You will go to the reaction time paired test tab. And this reaction test, I put the link here. Fun fact is actually still up from, gosh, it must be 20 years ago, like 20 years ago when I used this myself as a science fair kid. I used this exact online reaction time test for one of my projects. And it is still there, which is just astonishing to me. Way to go, UW. You've done a great job creating this. But this is so simple to use with your students. It requires literally zero materials. You just click on this and then you wait for the green light. And once you see the green light, you click it, right? And I did this with students in front of the class. I had it hooked up for my computer and I had students come up one by one to do it just because it created a little bit more fun, a little bit more sense of competition. It just made it more engaging for them. But yeah, you do this 5 times and it'll continue to collect the data for you. And it even provides an average for you. But you can also do that um on the Google Sheets as well. And final trial there. So then we've got these just as an example. So it'll do 5 trials for you. And then if you want to start over, you can click that. It'll start over. So that's how that works. And then what I would do for the paired example, that means that it's the same group of people, or in this case, the same person, just you, that's doing the two conditions that you're comparing. So first I did it with no phone, right? And I had my 5 trials. And then the sheet that I linked for you that I showed you on the slide, it goes through what all of this means and how to do that in the Google Sheets. So definitely take a look at that. Just for the sake of time, I'm not going to go through all of it right now, but you can access that to look at it and find out. And feel free to reach out to me as well if you would like extra help. But then what I would do is, okay, get out your phone. And this is a real world example, right? Or I would provide them a video on my phone or something like that. And this is a real world example, right? Where they need to to know their reaction time is not as fast if they are distracted by their phone, right? And we've all been behind that person at the stoplight that they're clearly on their phone or something. They don't realize it turned green. And so then this just really demonstrates it. And so with my example, you can see here, then I did actually do this myself. That my reaction time was significantly slower when I was looking at my phone. I think I was watching a video on my phone. And even though I was holding my phone up here, it was still slower. And so then I was able to get these two different means here where you can see it's a lot slower. And I've also graphed it as an example so you can see that yes, the reaction time was a lot longer with the phone compared to no phone. And how you can then, and I'll just go ahead and copy this over for the sake of time. I'll copy this over to this sheet where you would be practicing. And what you do here, you find the means. So you do equals average, right? And sometimes a Google Sheets will actually predict for you and pretty accurately, but you can just double check. Do I actually want B2 to B6? I do want B2 to B6. Okay, perfect. Thank you, Google. And it has done that average for me. So once again, it's equal average. And then once again, it's guessing for me that I want C2 to C6. That is absolutely right. But if you wanted to, you can also drag it, close parentheses, enter, and you can do it that way. So then I've got those two averages, and I actually just realized I didn't need to do that for the t-test. I just need to do that for the graph. But that's okay. Now you've gotten an example of how to do those means. Now for the t-test, to get our p-value, right, which we're hoping is less than 0.05. We're going to do equals t dot test, and you need to click this here when it says t-test. And then you're going to um, put your first range. So you're going to highlight your first range here, and then you're going to comma, and now range 2, this one here, and you're going to comma again. And then it's asking you for your tails. So in general, essentially two-tailed versus one-tailed. One-tailed, if you feel really confident that the data should only be skewing, that the difference should only go in one direction, you can choose one-tailed. Generally speaking, though, two-tailed is considered the more rigorous test, so that's what I recommend. It allows for the possibility of your results actually going in either direction, either being greater or less than what you expected. So let's see, or than the mean you're comparing it to. So we'll do 2 for the two-tailed, and then finally type. This refers to the type of t-test, paired, which is what we're doing, paired, and then two sample equal variance, so that's the unpaired. If you expect that the range is about the same for both of them, then you do that one. In general, though, you would do the two sample unequal variance. So for example, with my 10th grade versus 11th grade, I would do two sample unequal variance. But for this one, we are doing paired because it was the same person both times, and close parentheses, and there we go. And I have a p-value of 0.037 or 0.038. And you can do the sig figs on it and everything, but it looks like we went out to 3. So in any case, all to say, you have a p-value that is less than 0.05, which means that you can reject the null hypothesis. And there is actually a statistically significant difference between having no phone and trying to your reaction time with no phone. There's a statistically significant difference between your reaction time with no phone and your reaction time with your phone. At least that's true for me. And it seems like it would likely be true for the general population as well. Um, and that is an example of how to do a t-test really fast, quick, and easy using Google Sheets, which is really helpful. So that brings me to the end. And I actually will go ahead and add, because I realized I forgot to. Here's my email, lbingman@societyforscience.org. Please reach out if you have any questions. If you would like me to send you any additional resources, or it's not working for you right, or you're confused by anything, I would be more than happy to help you figure it out. And I wish you the best of luck. Oh, one final thing I'll say. Obviously, whether you're doing these statistical tests or not will be heavily dependent upon the age level and just you know your students best, right? I think that there's really simple ways to be able to make this accessible for your students. And if you're teaching elementary school, it might not be within their current mathematical kind of realm right now. And so just getting them started at least with making those graphs is a great way. Also, if it's kind of an in-between, is doing those error bars, like you can see on here, doing these error bars, which I explained in my making graphs in Google Sheets. And so you can absolutely have them make those error bars and compare the bars to each other as well, if that feels like something more accessible to them too. But thank you so much again. I hope you have a really great rest of your day and hope to see you and your students' projects and see the amazing work that they do. Bye. And